Hi everyone, today we are going to talk about Newton's second law. And in this measurement, first let's introduce about the Newton's second law. It tells us if there is an actual force applied on the object, and the object's acceleration will be produced, which means the velocity of the object will change. And if we write down an equation for this kind of relation, Newton's second law tells us the acceleration of the object equal to the net force you applied on the object divided by the mass of the object. Since force is a vector, acceleration is also a vector. The direction of the acceleration is the same direction as the net force. And the unit, since we know the unit for force is Newton, and the unit for mass is kilogram. So the unit for acceleration is Newton per kilogram. Or you can also write as meter per second squared. So for this measurement, we are trying to figure out what is the relation between force, mass, and acceleration. Based on this formula, we can see it tells us if the net force, if we keep one of them as a constant. So for example, if we keep the mass of the object as a constant, so then if the net force increase, then the acceleration will increase, which means acceleration is proportional to the net force when the mass is a constant. When the net force is a constant, so look at this equation. It tells us if the net force is a constant, then if mass increase, then acceleration will decrease, which is telling us acceleration is inverse proportional to the mass of the object. So today we are trying to prove this result based on our measurement. So on our measurement setup, we have a sensor which can sense the motion of this object, which is a cart. And on the other side, there is a pulley attached with a hanger. The hanger is about 50 grams. And we need to know what is the mass of this cart. So the mass, the cart, and the hanger, they become one system. So in this system, in this setup, the only net force on the system is from the gravity of the hanger side. So the force of gravity on the hanger side is the net force for this system. And the total mass in the system is whatever the mass on the cart plus the mass of the hanger. Then that is the total mass. For the system, we have mass of the cart plus the mass of the hanger. So now, if we know the gravity force of the hanger side, and we know the total mass of the system, then we can calculate the net acceleration for the system will equal to the force of gravity from the hanger divided by the total mass of the system, the total mass on the cart, plus the total mass on the hanger side. So this is the acceleration in this measurement setup. So for the measurement, what we are going to do is to prove when there is total mass is a constant and this acceleration is proportional to the net force. So we will set up this measurement like this way. First, we will apply 220 grams on this cart. And so now for the whole system, you know the total mass is 220 grams plus the mass of the cart and plus mass of the hanger. Our first measurement is we will run like this with this 50 grams of hanger, and we will measure what is the acceleration in this motion. And now the second measurement, we will remove one of this 20 gram. So we move one of the 20 gram on this hunger side. So now in this setup, as you can see, the total mass of the system is still the same. It's still 20 gram plus card plus 20 gram plus hunger. So the total mass doesn't change. But the net force for the system now increased because we increase the net force on the gravity force on the hunger side. So now this net force increase. So we expect that the acceleration in the second measurement will be bigger than the first one. Now the third setup, we will move this another 20 gram of the mass on the hunger side again. So the total mass of the system is still a constant, but we keep increasing the gravity force on this hunger side. So we will measure 3 different accelerations from these 3 different measurements. We call it A1, A2, and A3. Total mass is a constant, but the net force keep increasing. So we expect in our measurement, we will have A1 smaller than A2 and then smaller than A3. So we will see if our measurement can prove this result. Our second measurement is similar, but this time we are trying to keep the net force as a constant, but we try to change the total mass of the system. So what we will do is, this time we keep this hunger 50 gram as a constant, which is the net force for the system. So we don't change the hunger side at all. In the first setup measurement, we just use this card without attaching any extra masses. So we run this measurement and measure what is the acceleration for this system. So the acceleration will equal to the net force from the gravity force of the hunger divided by the total mass of the card plus the total mass on the hunger. The second measurement will apply a 100 gram mass on top of this card. And so now we measure the second time what is the acceleration in this case. So you can see in this case, the net force is still the same, the gravity force of the hunger, but the total mass of the system increased. So for the second measurement, we expect that this A2 will be smaller than our first measurement. Then the last measurement, we will apply the third, another 100 gram mass on this card. So now again, the total mass of the system is increased, but the net force is a constant. So we apply this one, we measure this acceleration, we call it A3. So from this setup measurement, we got 3 acceleration. So we expect A1 will be bigger than A2, bigger than A3. Because in this case, our net force is a constant, but we keep increasing the mass. So mass is inversely proportional to the acceleration. So as our mass increase, the acceleration will decrease. So we will get this conclusion. So let's see our measurement now.
Okay, so here we are going to do this Newton's second law experiments. So this is the first part where we're just going to keep the total mass of the system the same. So first, we're going to measure the mass of our carts with 2 20-gram masses. So the total mass of our cart and 2 20-gram masses. Take this.
Oh, yeah.
And then 2 20-gram masses we'll put on top of the cart. Okay. And so 200 grams. 100 is too much. Okay. 220. 230, 240, okay. So 230, okay, so that's going to be 236.85. I'm just estimating at that 0.05 because it's in between the 0.8 and the 0.9, so I'm just going to say it's 0.85. Total mass of our hanger is going to be 50 grams for the first run, since it's a 50-gram hanger. And so we're going to do our runs. So the first run is just going to be with both 20 grams on our cart and no extra mass other than the 50 gram on our hanger. Okay. Okay, so that's our first run. You can see that the velocity has a somewhat linear increase, meaning a constant acceleration. So we're going to do this again with a change of masses. So we're going to keep 20 of the masses on our cart, and we're going to take the other 20 and put it on our hanger so that the total mass of the system is the same. And we'll go ahead and do the second run. Okay, and again, you can see a somewhat linear increase in the velocity, and we'll be measuring the acceleration later. And for our third run, we're going to be taking all 40 grams, both 20-gram masses, putting it on our hanger, keeping nothing on the cart, and we're just going to do that by itself for our third run. Okay, so this is our third run. So our run number 2, the total mass of our hanger plus the masses is going to be 70 grams. Run number 3 was going to be 90 grams since it was 50-gram original hanger, and then we added 2 20s for the next couple runs. So we have that. We're going to be determining our slopes, which is going to be the acceleration of our runs. So run number 1, we're just going to be looking at this first part here. This is where it's increasing its velocity, and then it hits the bumper and rebounds. So we're only going to be looking at this first part here. So we're going to take our tools. So this one's going to highlight a region of our interest. And then we are going to fit a linear line to that. Which we're going to take linear. And so that gives us a slope of 1.47, which is equal to the acceleration of our cart. So that's 1.47 meters per second squared acceleration. We'll select our second run. And again, highlight our region of interest. And our slope is 2.29 meters per second squared. And then for our third run, we have 2.80 meters per second squared for our acceleration. So now that we have our experimentally calculated acceleration, we're going to go ahead and we're going to have you calculate what the theoretical acceleration is. So total mass of our hanger, like I mentioned, is 50 for the first run, 70 grams for the second run, and 90 grams for the third run. you're going to calculate the net force by multiplying our mass by the acceleration due to gravity to calculate our theoretical. And then from that, you can calculate our acceleration and compare the two, our theoretical and our measured acceleration using the equations you used before or learned before during the lecture part. So we're going to leave that for you to do, and that ends this first part of Newton's second law. Second part, we're going to continue on and do where we are continuing adding masses to the cart, but keeping the hanger the same. So we'll begin that soon. Okay, so here we are for Newton's second law, part 2, where we're going to be leaving the mass on the hanger the same, but we're just going to keep adding masses to our cart. So the total mass of the hanger is just going to be 50 grams, since that is what the hanger is. It's a 50-gram mass hanger. And we're going to measure the total mass of the cart to start with, and then we're going to be adding masses after that. So the total mass of the cart is going to be so it's going to be less than 200. 100, 150, 170, 190. Okay. So we're looking at 197.25. And so the reason for the 0.25 is because the reading is between 0.2 and 0.3, so I'm guessing, estimating around 0.25. Okay, so I had measured the mass of the cart, which is 197.25. We are then going to do our 3 runs. So first is going to be without the mass. Second is we're going to add 100 grams to the cart. And then the third, we're going to add another 100 grams to the cart, leaving the mass on our hanger exactly the same. So first, we're going to do the measurement without the mass. You can go ahead and do that. Okay, so this is our first run. As you can see, we have a nice linear increase in velocity, linear acceleration like we expected from before. Now we're going to add 100 grams to our second cart, or to our cart, and measure our velocity with that. So our total mass of the cart is now going to be 297.25 grams. Okay, and we're ready to start. Okay, so that is our second run. We'll do the one last run with another 200 grams, or adding an additional 100 grams, so a total of 200 grams onto the cart. So 397.25 will be our final mass of the cart. Okay, so even though the run wasn't necessarily perfect, we still have this linear increase in our velocity that we can use to calculate the acceleration, even though the cart got a little stuck due to the added mass of it. So we're just going to go ahead and use that. So if we go on to measure our velocity, our acceleration, like we did in the first part, we'll select our data set. So the first run, take our little box to highlight the points that we want. Okay, and then fitting a linear line. You get a slope of 1.75 meters per second squared. Okay, our second run. we get a slope of 1.01 meters per second squared. And for our final run, we have we're just going to take our region here before it stops slowing down. So we have a 0.179 slope, which is reasonable since we're doubling the mass every single time, and our acceleration is decreasing by a reasonable amount as well. So with that, we have our experimental results for our acceleration. We're going to again leave you to do the theoretical acceleration with our given masses of our carts. The total mass of our hangar is 50. And then you're going to again compare our measured values to the theoretical ones that you are calculating and give a percent difference between the two. So that is all for this experimental parts of the Newton's second law. Yeah.